All right, and we're back. Thank you for your patience. Let's just let this stream settle down, and now we should be good to go. I'm gonna hop right back into the session, and we're gonna start off with question number 14, which unfortunately has the answer there, and I cannot hide it. But nonetheless, what is the Lewis structure for C2H7N? Now, for this question, we definitely have to recognize what group is here. Okay, this is a, I guess, it's an organic compound. And we have the C2, right? Well, we say H7N. Typically, for ethane, it would be C2H6. All right? Because it would be 2N plus 2, which would make sense. But instead, what's happening here is that there's a nitrogen. What nitrogen is done is that it actually replaces a hydrogen, so it'll be C2H5N. But the nitrogen also comes with its own hydrogens, which would be NH2. And you will notice now that the H5 and the H2 added to the H7. So what we have here, the reason why I'm doing it like this, although it's unorthodox, is because I want to highlight that we actually have an amide group, all right? Or amine, sorry, not amide, an amine group, okay? And the reason why that's important because now our structure looks like this. Sorry, better picture. Where each, I guess, bend is a carbon, and nitrogen will be at the end with this lone pair like that. This is what would the structure would look like if we were drawing like its, I guess its bone structure. I believe that's what it's called, something like that. Where it's kind of just its most simplified form. But here it's not asking for this, it's asking for its Lewis structure. So let's actually translate what we have here into a Lewis structure, which is actually going to look a lot like the picture. Almost actually exactly like the picture. So we have the C, C, N as to start. Then we have the lone pair as we discussed. And now we have like that, because remember C2H5, 1, 2, 3, 4, 5, and then the N with the two H's there. All right, and let me just move this down a little bit if it would let me. Doesn't look like it wants to. There we go. Moved a lot more down than I expected. Nonetheless, we have it there now. With the H, 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 H. This is what we're working with here. And now we can actually do a few things here to verify whether or not we actually have the right structure. First of all, let's find out if we're using the total amount of electrons properly. Carbon, that'll be 4 electrons for each of them because that's their valence shell. So that'll be 8 electrons that carbon contributes. Hydrogen is 1 electron each, so that'll be 7. And then 1 nitrogen is 5. So 7 plus 5 is 12, plus 8, that's 20 electrons total. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 bonds and 1 lone pair. So that's 10 pairs in total, which is indeed 20 electrons. So that part's satisfied. But what about the octet rule? With a quick glance, for the 2 carbons and nitrogen, that is also satisfied. And what about the last thing, the formal charge? So for a carbon to have a formal charge of 0, it usually takes on the form of having 4 bonds, which is what it's doing here. Nitrogen, it needs 3 bonds and 1 low pair, which is also what it's doing here. So both of these are following a formal charge of 0. And the hydrogen, the last one, is just 1 bond, which is also what every hydrogen here is doing. So all these have a formal charge of 0. And so we can say without a doubt that this is probably the best Lewis structure for C2H7N. And this is correct. So we have Sorry, I do apologize for that. If I can just erase that. There we go. Does not look interesting. Alright, so nothing wants to erase, but we do at least have the black back. Okay, so let me just scroll up here. Oh, it won't let me. So just hope that these are erasing. So thankfully they are. So number 15. For number 15, we have write one Lewis structure of N2O5 and what are the bond angles around the central oxygen atom and the two nitrogen atoms, and what is the hybridization of each. So N2O5, they did give us a good hint, thankfully, where it's O2 NONO2. So the skeleton structures like that, we theoretically have, sorry, let me just say N2O5 Lewis. Okay, so it'll be O2. Well, let me just start with the NON. N-O-N. And then we have the O2. So I picture something like this in my head. Okay, so that's definitely a great start. For N2O5, we need a total of, well, for nitrogen, we have 5 electrons each for the valence shell, so that's 10 electrons. And O5, we have 6 electrons each times 5, that's 30. We're working with 40 electrons total for this compound. So with that being said, let's start filling out the outer shells, well, the valence shells left over. So you have 1, 2, 3, 4, 5, 6. 1, 2, 3. Whoops, that's too many electrons. Because it's sharing one of its 6, so it actually be 2, 3, 4, 5, 6. So just like that for everything else. 2, 3, 4, 5, 6. And the same here. This one's actually sharing two of its 6. So it'll be 3, 4, 5, 6 like that, which is perfect for it. And the same thing here. 2, 3, 4, 5, 6, and 2, 3, 4, 5, 6. And now for the nitrogen, it's actually showing 3 of its 5. So it'll be 4, 5, and here again, 4, 5. So now the question is, how would we then distribute this to where this would make sense? So funny enough, the Lewis structure here that would allow nitrogens to still follow the Octet Rule, but allow the oxygens also to follow the Octet Rule without, adding unnecessary double bonds, the nitrogen wouldn't form a double bond with each oxygen. What would happen instead is that the nitrogen would form a double bond with one of them and just give the electron to the other one. So this is what I'm picturing here. One of the electrons from nitrogen will do this, form a bond, okay, and the other nitrogen will just be given. If only there's a way to draw a better picture to get around it. I'm just gonna do it like this. So I'm gonna actually erase that and reposition this. There we go. And this is what's happening here. Alright, this is actually what's going to happen. And the same thing's going to happen exactly on the other side. So with that being known, I'm actually going to reposition it right now. Actually, now I'm going to make it go on the top one instead. Because I just want to show that this is just one, as I said, one of the possible Lewis structures here. There's other Lewis structures possible for each one. Alright. So with that being said though, one is going to go into the bond, okay, like that, and then the other one is just going to give it to the oxygen. So with that being said, we now have this form for this molecule, O, N, as I said, still a single bond here, but this is going to be like that. And this right here is a double bond. And we also have the same thing here, the N, and this would be, just trying to draw that all out. Okay. And if we just, I'm just gonna think something in my head real quick of the possibilities. Okay, yep. And now, I hope I didn't, no, I didn't do this correctly. This would be the double bond here. This would be the single bond here. And this would be what that looks like. And then 1, 2, 3, 4, 5, 6. So this is a structure we're working with. Quite a complex structure. In fact, it has so many different types of resonance structures, it'd be a hassle to draw through all of them. But there is one thing I do want to emphasize though, is that if we actually first look at the total number of electrons, so hopefully here we actually do have 40. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 lone pairs and 1, 2, 3, 4, 5, 6, 7, 8. 8 bonds. So in total that's 20 pairs, which does indeed add up to 40 electrons. That's perfect. What I do want to stress though is the formal charge. The reason why is because we only have nitrogen and oxygen. Nitrogen's formal charge of preference is 1 lone pair and 3 bonds. But that's not what's happening here in this picture. Both nitrogens all have just 4 bonds. For nitrogen to have that, its formal charge would have to have been +1. The reason why I say that is because what happens here is that when you replace a lone pair with a bond, you go positive, which is what happened here. But you're probably wondering that, wait, but this molecule is neutral, and yet we have 2 pluses. So we need 2 minuses, which actually is shown by the oxygens. The oxygens' preferred state is 2 bonds and 2 lone pairs. And not every oxygen is doing that. In fact, the ones up here and down here have replaced a bond with a lone pair. So that'd be 1 towards the negative side. So we have a negative here and a negative there. So although in total this would be a neutral atom, as you can see there are positive and negative parts to it. Now, as I said, much of this can go through hybridization. And it is quite intense how it can do that. And it's quite hard to keep up with. So let's just make sure that I am picturing this right in my head. Okay, yes. So the first thing they ask is, what are the bond angles around the central oxygen atom and the 2 nitrogen atoms? Okay, the central oxygen atom would have a bond angle of like, and this is where it gets a little bit crazy, because I could actually draw a resonance structure if I really wanted to where I moved this one out here, so that bond here, and moved this bond into here. Alright, and the same exact thing happened where I moved this out here and this one into here. The reason why I'm doing this actually is because we still get the nitrogen. I'm going to draw this a little bit lower. Just a quick method. This is a possible resonance structure. Very viable still. I'm sorry. Nitrogen. Where now, although it's a lot less stable, well, and you'll see why. Let me just reposition this. This is what we're working with now. We still theoretically have 40 electrons, so we have 3, 6, 9, 12 electrons on each end, and 1, 2, 3, 4, 5, 6, 7, 8 bonds still. But as I said, now for this oxygen in the middle, it's gone ahead and done something very unfavorable. It's now replaced 2 lone pairs, 2 bonds. So this oxygen in the middle is now 2 plus. Okay? And nitrogen are still plus because they haven't changed. But we have 4 minuses. Now you're probably wondering why I went ahead to draw this structure. This is a possible resonance structure. Not very stable, but nonetheless very positive. And the reason why I drew this is because this emphasizes actually what's happened to the oxygen. The central oxygen atom and the two nitrogen atoms, because I was able to draw like this, we could actually say that it's almost mimicking a linear bond between the oxygen and nitrogens. What does that mean? It means that the angle around the oxygen atom could be pseudo or just around 180 degrees. Okay, and this ties into our hybridization, which we will get into, but that is a possibility right there, because if you picture resonance structures, they're always, it's not static, it's always interchanged, always moving. So with the oxygen, because we can draw like this, it would make the most sense to think of it as almost a linear bond between them, with kind of electrons moving in and out. At least that is what I picture. And now for the nitrogens, as you've seen, even when things are moving, it always has 3 points of attachment. Okay, so with that being said, this one would be around the nitrogens. For both nitrogens, it's around 120 degrees for each nitrogen. So what is the hybridization of each? The oxygen's hybridization, believe it or not, I would actually contest in this case, it wouldn't just be sp4. It wouldn't just be 2 bonds and 2 lone pairs, because the lone pairs are sometimes not there. The best thing to do is we pretend, let's say we put it in its most unfavorable position, which would be the 2+, which is still something that can definitely happen, to show all the ways that the lone pairs really could move around this molecule. And that's how we can say that for this, oxygen could be contested to say it's sp hybridized, due to the fact that we can actually get a 180 degree bond angle. It could be a straight line right there. So that would be for the oxygen. For the nitrogen atoms, because it's 120 degrees, we could say this is sp2. And we can actually check our Vesper theory here. 180 linear sp. That's what I'm picturing for the middle oxygen. For the nitrogens on the side, we're talking more about this, trigonal planar. I like to think of it as if we were to take away all the rapscallions, all the atoms that are moving about, the lone pairs, what we are really left with is just a linear structure in the middle and trigonal planar structure on the ends. Because if we were to just take these out, let's say if I do like just a bare bones, I'd be seeing this. If I didn't want anything to move, I know I would need at least this much with nothing moving. This is the minimum I need. Notice I don't have any lone pairs on the oxygen. This is why I would say the best thing you could say is as sp hybridized. Notice how the nitrogen has 3 things surrounding it. This is also why I would say the best thing is sp2 hybridized. So with this, I have a feeling, depending on how our colleague answers it, because this is definitely much more advanced, definitely getting into our organic chemistry level. But we'll see what our colleague has to say here. So it's like, this is the electron dot diagram. This is definitely not a bad start, but this implies that these 2 electrons on the oxygens will stay there. So with that being said, they do have this shape, which is a great start, but and let's see actually, because I don't want to jump too early, but they say the central O atom has 2 atoms bonded to it plus 2 lone pairs, therefore has a steric number of 4, which is 109.5, and I have an addition of sp3. So this is where they fail to acknowledge, is that those lone pairs may not stay on the oxygen. And that's the part I really want to stress with this question. As you can see, all the different possible forms of resonance structure is that even though we have so many formal charges, all the rules are still being abided by. The Octet Rule, check for the middle and for the nitrogens around it. it still has 40 electrons it's working with. So everything is still there, except now it doesn't have a lone pair. It could also have even been to a point where it had an oxygen just like that, and only one of them took the lone pair. So these are all possibilities, which is why I really wanted to draw the bare bone structure, which is down here, what I'm picturing in my head. So with that, I would say this is actually incorrect, because they don't even mention the nitrogen as well, and especially the nitrogen in this case would definitely not be 109.5, because it even points out here that they've gotten rid of their lone pair to form that bond. So with that being said, a lot more steps than you would think, but with this is incorrect. Due to resonance, and that's the part we really want to stress, is that this is actually due to the resonance structure. As it says, just write one Lewis structure. Due to resonance, the oxygen will be sp hybridized, and the nitrogens will be sp2 hybridized. The bond angles would be around 180 degrees for oxygen and 120 degrees for nitrogen. Now, to just make sure that I do understand this concept, what I do like to just refer to external resources. So N2O5 resonance structures, we should have a lot. Yep, just like that. This is just I don't know if this accounts for every one of them, but if we look at this picture here, although they have some unstable ones, the one I do want to find, it actually doesn't have even everything on it, because although this is +1, there should be one where it has even +2. If we were to now move this out and then move the other, like let's see if we can actually find a picture like that. Does not look like it, but it's like there'll be some that are stable, some that aren't stable. Now let's see here in terms of the actual question. N2O5 resonance hybridization. So this would be a YouTube video, and let's see here. This one would be, well, I guess we cannot confirm that, because not from that site at least. Okay. And with that, I believe that I've given up. I don't want to keep going through this because we have other questions we want to solve. So with that being said, I would actually also check with your professor as well. This is just my theory, at least, especially due to resonance structures. I'm still trying to get familiar specifically with the different possibilities of resonance structure, of what's allowed and what isn't. As far as I can see, this is a possible resonance structure as well, because everything still follows the Octet Rule. And so although it is going to be highly unstable and unfavored, this would be another possibility, and we can actually see how oxygen can end up being sp hybridized. But nonetheless, though, what they did unfortunately was incorrect. So now for question number 16, we have, what is the name of the conjugate base of H2PO4 minus conjugate base name? So first of all, we need to know what the conjugate base of this would be. So we have H2PO4. We would have to have it as the acid, plus H2O, which would serve as the base here in this case. And that would be liquid. And so now the HO will be taking a proton for it. So we have HPO4 2 minus plus H3O plus. So this is what we want to focus on here. The HPO4 2 minus. So what will be the name for this? Alright. So the given conjugate base H2PO4 is, oh, I went too far. I answered the conjugate base of H2PO4, but they're asking the name of the conjugate base H2PO4. So the formula they actually used was H3PO4 no minus plus H2O turns into H2PO4 now minus plus H3O. So with that being said, just give me a quick second. Just doing some calculations. Alright, just to make sure. With that being said though, this will also be the conjugate base. Both of these are, but they're only referring to this one here, so not the one above. So now let's try to name it though, just as how this question is asking for. They want the name of this conjugate base. So with that being said, and I know I say that a lot, just like how my colleague said, they do have dihydrogen phosphate. How do we get that? Phosphate is known as PO4 3 minus. Okay, that is a phosphate molecule. So if we have H2PO4, we would actually have 2 hydrogens. That's the goal here. And if we now split this up, it would be hydrogen phosphate. And then what we have to do is specify, because this is technically it's not an ionic compound, it's just a bunch of different non-metals together. We would actually have to specify the amount of hydrogens, the amount of phosphates we have. Luckily in this case, we have 1 phosphate still, but we have 2 hydrogens, hence why we have the di in front of it. That's why it's dihydrogen phosphate. And that'll be the H2PO4. If we have the first one, for example, this one will just be known as hydrogen phosphate. Okay? Or I guess even monohydrogen phosphate. But most likely it's just hydrogen phosphate. And I'm referring to the HPO4 2 minus. Okay? So with that being said, let me just check here. We have dihydrogen phosphate, just like how they did, and this would be correct. And now for question number 17. We want to draw a Lewis structure for calcium carbonate and magnesium hydroxide. So luckily you can see the calcium carbonate name. So for magnesium hydroxide, we're going to see if we can actually draw that without being given any hints. So calcium carbonate, Lewis, and magnesium hydroxide, Lewis as well. So for this, let me just double check what I'm thinking. The calcium carbonate, this one is known just how it says. Calcium is Ca, and you don't have to memorize this. Carbonate is CO3. And the key thing is about this CO3 is that it's 2 minus. And luckily calcium is 2 plus. Okay? So that's how we have just CaCO3, which is perfect. Now, I'm actually going to skip ahead and just do magnesium hydroxide as well. Magnesium is known as Mg, and it's 2 plus. Hydroxide, on the other hand, okay, is OH, just 1 minus. For this to balance, we need 2 OHs. So in reality, it'd be MgOH2. And this one here will be CaCO3. So now how would we draw these? So for these, because these are actually ionic compounds, I would actually start with the non-metal part, the CO3. That's what we have to first balance out for the calcium carbonate. So we have, since this is CO3 2 minus, okay, carbon would be 4 valence electrons, oxygen would be 6. 6 times 3 is 18, plus 4, that's 22 electrons, plus the 2 minus, we're dealing with 24 electrons total. So we have the carbon in the middle, and we have 1, 2, 3. O, O, O. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. And you're probably wondering why 5 is because the bond implies it's sharing one of its 6 valence electrons, so I just added 5 more. And carbon is sharing 3 of its 4, so just 1 more. And now, before we go around trying to make double bonds, we first need to factor in the 2 I guess extra electrons. So just put 1 here and 1 there. And now we can clearly see that there's only 2 pairs of unpaired electrons, which those 2 would then go ahead to form a bond, or an extra bond on the bond. So that would lead to now your picture looking like this. C, okay, double bond, single, single, O, 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 and we have now, well, it doesn't really matter how we do it, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And this would just be one of its many resonance structures. And to support that, not only do we have 24 electrons, so we have 1, 2, 3, 4, 5, 6, 7, 8 lone pairs, and 1, 2, 3, 4 bonds. So that's 12 pairs in total. So it is indeed 24. And we can also see how we got its charge by using the formal charges. Carbon formal charge is 0, likes to just have 4 bonds, which is what it's doing here, thankfully. And oxygen, on the other hand, likes to have 2 bonds and 2 lone pairs for it to be a formal charge of 0. So in this case here, for this oxygen, the top one is fine, but those 2 sides have actually replaced a bond with a lone pair. For that to happen, actually, when you replace a bond with a lone pair, you actually go 1 negative. So it would be a minus and minus. And coincidentally, there you have it. This is how CO3 carbonate is a minus. And this would be the non-metal side. So I'm actually going to pair it together like that, just like this, and this would be the 2 minus. And now for the metal side, we just have calcium. So it's just going to be a nice small little, well, not small, but you know, calcium right here, and just 2 plus. This would be the Lewis structure for it, considering that this is an ionic compound. There's no real bonds to it. It's just a metal with a non-metal, kind of like that. So this will be what we get for CaCO3. Now for MgOH, or MgOH2, that one, okay, we have to first do the OH. Oxygen, that's 6 electrons. Hydrogen is 1, plus another one from the minus, that's 8 in total. So we have OH. I'm just going to actually stick with the same colors here, actually. So let me just do that. So we have oxygen, hydrogen. Or actually, maybe just better yet. Nope, this is fine. And for this, we're now going to fill in the rest. We have 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, whichever one. The point being that the oxygen right now is incomplete until we add the extra electron from the minus. And that would really be it. And we can actually see here that just like the one above, that's how oxygen has that negative charge. So that would be just, unfortunately, one of the OHs. But magnesium, which we're working with in the middle, needs 2 of these. So it'll be 1 there and just 1 on the other side. Something like this. And sorry, I definitely forgot to add the 2 plus for the magnesium. So your Mg2 plus. Oops, wrong color. And just so we don't also forget, this will be a minus. And sorry, move this aside. This will be a minus, will be 2 plus. And this, sorry again. There we go. 2 plus, minus. 2 plus, 2 minus. There we go. So these would be the theoretical Lewis structures, because once again, it's not really about bonds because these are ionic compounds. So we kind of just like situated next to each other as far as I can remember for Lewis structures for ionic compounds. So let's see how we did for this question. They do say it's MgOH2 for this one. So the Lewis structure for this, magnesium hydroxide, oh, that's strange. They definitely skipped over CaCO3. But Lewis structure is Mg2 plus and OH minus, OH minus, which is what we've done here. So that's perfect. And they are missing the CaCO3. I think they were supposed to be right here, but they may have put something else. But I would say that this is correct. They do have the concept down in this case, because of the fact that we pretty much got the same calculations for the valence electrons for the CO3 minus, and the same thing for these oxygens that were just 8, and there's 2 of them. That's how they got 16. So at least they have the concept down. So now for question number 7. Is this 17 already? So this is question number 18. And for question 18, we have draw a Lewis structure for PF3 in the box on the right, including the lowest pairs. So PF3 Lewis. So for this question, we have a phosphorus, which is on the 15th column. So that'll be 5 valence electrons. And the fluorine, which is on the 17th column, and that would be 7 valence electrons. Together, PF3, well, first we need to make sure we multiply 7 by 3. That'll be 21. So that's 21 electrons total from the fluorines. Plus 5, we need 26 electrons total. So we have phosphorus and 1, 2, 3. Or better yet, maybe we better just do like this. And you'll soon see why I chose this shape. So with this, we have a fluorine, fluorine, fluorine. And we're now going to fill in the rest of these. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. I don't know why I didn't just put 6. I guess I was still thinking of oxygen. But fluorine is sharing one of its 7, which is why it gets to fill its octet with the rest of the valence electrons. Phosphorus, on the other hand, is actually sharing 3 of its 5. That's why we have 4 and 5, which is another reason why I drew it like that. So in total, do we have 26 electrons? Let's see. We have 10 lone pairs and 3 bonds. So that's 13 pairs in total. That is 26 electrons. And now, are these all with a formal charge of 0? Fluorine's formal charge is typically 3 lone pairs and 1 bond. So let's check. Phosphorus is 1 lone pair and 3 bonds. Also checked. That's for the formal charge of 0, which they all do. So this would indeed be the Lewis structure for phosphorus tetrafluoride. Let's see what they got. And that would be correct. Exactly, actually. So that's convenient. So this is correct. And we are now good to move on to the next question in this set. Question 19. So for question 19 is asking, what is the total number of valence electrons for hydrogen, cyanide, or HCN? Total valence for HCN. So for this, we kind of need the Lewis structure then, if you think about it. Or do we? Maybe we don't. Just the count. So with this, total valence for HCN, we're going to actually ask for the valence electron each one contributes. So hydrogen contributes 1 valence electron being on the first column. Carbon would contribute 4 valence electrons being on the 14th column. And nitrogen would contribute 5 valence electrons being on the 15th column, according to the periodic table, which I am just going to double check with right now. And yep, that is correct. So 1 plus 4 plus 5, we have in total, let me see here, 10. Sorry about that, just had to think for a second. So you have 10 electrons total. That's actually would be what we consider the total valence electrons we're working with to draw this Lewis structure. And this Lewis structure looks something like this. And as you can even see here, we have the 2 lone pairs on nitrogen, and we have 4 bonds. I mean, the 1 lone pair on nitrogen and the 4 bonds, so that's 5 pairs in total, also 10 electrons. So this is actually going to be the shape. So with that being said, yes, the total valence electrons for HCN is 10. Unfortunately here, as you can see, I do have 9 instead from our colleague, which would be incorrect. Total is 10 because it seems that they thought nitrogen gives you 4, but instead it gives you 5. It's always good to just double check and make sure you're always referring to what column they're in, because usually the column they're in tells you the amount of valence electrons they will have. So with that, that is incorrect. And then let's move on to question number 20. Okay. So with question number 20, we have what is the Lewis structure for AlH3? So Lewis for AlH3. Okay. So for this, the Lewis structure for this, we have to first go ahead and draw out, well, I mean, first count the total valence electrons, similar to what we just did. Nonetheless, let's see. Aluminum, being on the 13th column, has 3 valence electrons, and hydrogen on the first column, 1 each, so that'll be 3 as well. We're working with 6 electrons total for this. So we have Al, and then 1, 2, 3. H, H, H. Now hydrogen is already using is 1 of its 1, and aluminum is funny enough already sharing 3 of its 3. So really, this will be it. We can actually even check the formal charges as well by just drawing out what aluminum would be in this case, and it just be 3 bonds, because that would be its representation of a formal charge of 0, which is what it's doing. And hydrogen would just be 1 bond, which is also what it's doing here. And we also know we have 6 electrons, we have 3 bonds, so 3 pairs, 6 electrons. So this will actually just be our Lewis structure for AlH3. It is trigonal planar, very flat, just 120 degrees from each hydrogen, and that would be all there is to it. And let's see what we got here. And exactly, AlH3, just like that. So this is correct. And now we can move on to question number 21. So for this, we have, what are amphoteric substances? So just like how our colleague said, amphoteric can act as an acid or a base. And the one they give that I'm really happy they give actually is water. Water serves as a conjugate base or a conjugate acid, as in it can donate an electron to get it can donate a proton to get its conjugate base, or it can take a proton to get a conjugate acid. So that's actually a really good one. I love using water as well, because water can go from this to a hydroxide or to a hydronium. Okay, that is a perfect example of amphoteric substance, where it can act as an acid or a base based on where it is based on where it is on the sheet here. Okay, as you can see, water overall is quite the weakest base, because it is just neutral pH pretty much. But exactly, like all these things here, it can react with and serve as an acid or a base. Now, here's the really cool part about this, is that water is not the only one. Another example of amphoteric substances are, think of substances that have two hydrogens, okay? But now let's take one hydrogen away. So think of things, I guess let me rephrase that have a minimum of two hydrogens it can give away. Things that I'm thinking of are, for example, H2SO4. Okay, I'm writing this on the side and you'll see why soon. H2CO3, H3PO4, H2. Let's just stick with those. Those are the ones I can think of on the top of my head. Point being, though, is that now I would actually put the H2SO4. Let me actually, if I can do this, actually, I'm just going to make this one red to signify that it is the one that changes. So I'll put H2SO4, give away 1, and now we have HSO4 minus. Give away another, and we have SO4 2 minus. HSO4, hydrogen sulfate, is also an amphoteric substance. Same thing with HCO3, which is what will happen when this gives away 1. And then when it gives the other, it would be CO3 2 minus. Now my favorite one, actually, this one's really cool, H3PO4, because it actually has two amphoteric substances when it keeps going from acid to base. And that would be H2PO4 minus and HPO4 2 minus. And then we have PO4 3 minus. So, as you can see, the list can go on. As long as you can find something that has at least 2 protons and you take away 1, then that one that you now just did, that conjugate base, is an amphoteric substance, just like how we've just shown here. Because these all can act as acid or a base depending on what it reacts with or what situation it's in, to where it can serve either as an acid or a base. If I even go back to my sheet here, I'm sure I can even find more. Like, for example, I see here oxalic acid. I think exactly based on this, it now turns to HC2O4. And if I could find oxalic part 2, exactly, this counts as well as a so it'd be like hydrogen oxalate. That would be a amphoteric substance. Same thing with sulfuric acid, sulfuric acid, also amphoteric. I think even arsenic, for some reason, also serves as amphoteric. So there's just a lot of examples here as amphoteric. The key thing being is that when it has more than one hydrogen can give away, so 2 or more, and typically the in-between structures are what is considered amphoteric. So this is correct. And now for question number 22. So for here we have what is the Lewis structure and its resonance structure of the sulfite ion. So we have SO32 minus. So Lewis for SO32 minus. So for this, once again, we're actually going to figure out how many valence electrons we're working with in total. So sulfur will be 6, being from the 16th column, and oxygen would be 3 times 6, that would be 18. So 6 plus 18, right now we're working with 24. And then plus that minus 2, we have minus 26. 26 electrons. So we would put the sulfur in the middle. And 1, 2, 3. Oxygen, oxygen, oxygen. And then we have 1, 2, 3, 4, 5 more of the 6, because the other 6 is being in the bond. And 1, 2, 3, 4, 5. So there we have it. Okay. And now what we want to do is, let me just double check here. The sulfur is sharing 3 of its 6, so it'll be 4, 5, 6, something like that. All right. And it is 2 minus, so I will go ahead and now add those 2 minus to make sure this one doesn't need a bond anymore and this doesn't need a bond anymore. So what's happening now is that these 2 unpaired electrons will come together to form a bond. So the Lewis structure for this will be S. And remember that sulfur does break the, I guess, the octet rule. But it also doesn't have to, and I'll show you what I mean after this. So we have, as a possible resonance structure, so 1, 2, 3, this is a possible resonance structure. Okay, as you can see here, 26 electrons. We have 3, 6, 9 lone pairs plus 1, 2, 3, 4. So that's 13 pairs in total. And so we do have 26 electrons. Now, as you can see with the formal charges, the oxygen, well, sulfur likes to have 2 lone pairs and 2 bonds like this. Okay. And instead it has, it looks like 1 lone pair and 4 bonds. So what really happened is that one of the lone pairs turned into 2 bonds. So it still has a formal charge of 0. The oxygen likes to have, though, also 2 lone pairs and 2 bonds for its formal charge of 0. So in this case here, actually, the oxygen, if I'm reading this correctly, would be good for the top one, but the other 2 from the left and the right actually replaced a bond with a lone pair, which puts it 1 more negative. And that is actually how SO32 minus has that charge of 2 minus. Now, for these formal, resonance structures, there's a lot of ways I can draw this. This will just be one example. I could have actually moved this out here, the double bond out to the oxygen. It doesn't really favor the sulfur, but now, funny enough, the sulfur now follows the octet rule because of its lone pair on it. So now it would actually be sulfur like that, and it would be, sorry, I'd actually draw a different color. There we go. And now we would have 1, 2, 3, 4, 5, 6. And now the sulfur actually would be one of the pluses. because it got rid of a whole lone pair, and this would now be 3 minuses there. Because this is asking for just its resonance structures, so I'm guessing it wants all of them. So this is just one of its resonance structures, okay? And now, with that being said, one of these oxygen bonds could have moved in here to form a double bond. So now we're back again to, well, not back, it will be slightly different to where we have this O, double bond S, single bond O, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. And now, what could have also happened instead of this, like when you go back, it could have done this instead, which is pretty much the same thing here, but now the double bond is on a different oxygen. So now we have, whoops, now we have this 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. So this is now what we have, and exactly. So to get to the middle again, what happened here was that this went, oh shoot, almost forgot. The sulfur always has a lone pair on it. Cannot forget that. So exactly. So this double bond now has to go back out. This double bond here has to go back out. But these are the Lewis structures here. As you can see, even the sulfur in the center, like the one here, although it's unfavored, and let me actually now fill in the charges quickly of what they could be. As you can see in the middle one, there is really no other way really for it to move, because it really doesn't want to. A lot of things would not favor it anymore. I'm trying to figure out the best ways to approach this. What could have happened as well is that, well, it wouldn't happen, but just an example, for this double bond to move in as well, and we have this, although it may seem like a possible thing, there's literally almost no benefit of doing this shape, because now the sulfur would be the negative one in the center, and because the oxygens are the more electronegative, they wouldn't really want that to happen. But those are also technically possible resonance structures. So I may just, go ahead and add that. So might as well be as thorough as possible here. So we have now, well, this. Okay, there we go. And this will now be the negative. And then if we even move this in here, you could also just have triple bonds and everything, along with this lone pair. Just because sulfur does unfortunately break the octet rule. So even something like this would be a possible resonance structure. So there's a lot of resonance structure. But I do want to focus on these 4, just because the one in the middle here, although it has a positive sulfur, it would be a shape that does at least follow the octet rule for everything. And the ones on the side, they're kind of like close, but not exactly it. So we have, yep, bond here, bond there, and bond there. So the reason why they didn't include the middle one is just because it is quite unfavorable compared to these 3 at least. Because you can see we have more formal charges. Hence why also this one will be unfavorable as well. Because it's not about the more formal charges, it's just the formal charges are on things where it could be instead on other things, if that makes sense. It shouldn't be, the negative shouldn't be on the sulfur, it should be on the oxygen. And here would be like 2 minus on the sulfur, which is definitely not favored at all. So with that being said though, this is correct. I do wish the question specified on the most optimal formal charges. I mean, on the most optimal resonance structures, because in that the case, then it would actually only just be these three, because they have the least amount of formal charges, and the charges are on the preferred atoms, which is what we wanted. So had that been clarified, this has probably been more of the picture we got in. With that being said, though, this is a good place to stop it. Question 22. Oh, apologies again. What I will do here is change it over. So, with all that, I just want to thank you again for joining me this evening. It has been lovely. With all the questions that we covered today, if you have any, if you want any further clarification or just looking for some tutoring, please, I ask that you check the links in the description below. We have fantastic tutors there. But with that being said, you have a great